Today I'm going to tell you about the equilibrium potential. I'm going to tell you what it is and how it is generated. Every cell is a battery because the inside of the cell has an excess of negative charges and thus its interior is negative relative to the outside. The battery is the power source for the action potential, and the action potential is the universal language of all nervous systems. But what exactly is the battery and how is it generated? All cells have different concentrations of ions in their cytoplasm compared to the extracellular fluids. The cytoplasm has a high concentration of potassium ions and a low concentration of both sodium and chloride ions. The extracellular fluids, in contrast, have low concentrations of potassium but high concentrations of sodium and chloride ions. Potassium is the main ion for establishing the battery. Here I show how the concentration difference of potassium ions between the inside and the outside of the cell generates the cell's battery. Since the inside of the cell has a higher concentration of potassium than the outside, potassium tends to diffuse from the inside of the cell to the outside. So the concentration gradient drives potassium ions out of the cell. The concentration difference is a force. It's similar to a pressure difference that drives molecules from a region of high concentration or pressure in the bottle on the left to a region of low concentration. This concentration difference acts just like the pressure difference that drives the spurt of champagne as the bottle is opened. To illustrate this, I'm going to fill the container in this figure with water. And then I'm going to separate the container into two equal parts with a semi-permeable membrane, which only allows potassium to pass and blocks all other ions, including chloride. Then I'm going to do something very simple, in fact very oversimplified. I'm going to drop one molecule of potassium chloride into the left side and 8 molecules of potassium chloride on the right side. Now I just point out to you this would also create an osmotic imbalance. That is, water would tend to be driven from the left side to the right side, but we're going to ignore the osmotic pressures and the movement of waters. We're just going to focus on the movement of ions. Because each molecule of potassium chloride will dissociate into two charged ions, a positively charged potassium and a negatively charged chloride ion. Notice that the number of potassium and chloride ions in the left side are equal, and thus there is no charge imbalance in the left compartment. There's one potassium and one chloride. The same is true of the right compartment. There are 8 positive potassiums and 8 negative chlorides. Chloride cannot pass through the pores from the more concentrated side in the right compartment to the less concentrated side in the left compartment because we made the membrane impermeable to chloride. But it is not impermeable to potassium. It will pass potassium. And because potassium is more concentrated in the right compartment, potassium is driven by the concentration force from the right into the left compartment. And when a potassium moves from the right compartment to the left compartment, it transfers a positive charge from the right into the left compartment, thereby making the left side more positive than it was before and the right side more negative. The left side has gained a positive charge, a positive potassium, and the right side now has an extra negative charge, an extra negative chloride. So the right side has 2 potassiums and 1 chloride, one net positive charge, while the right side has 7 potassiums and 8 chlorides, 1 net negative charge. The concentration force continues to drive potassium from the right into the left compartment, each time leaving an extra negative chloride behind. There it goes. And bingo, there goes another one. Now the right side has become increasingly negative because of the 3 chlorides that are not balanced by potassium due to the loss of potassium. So now the left side has 4 positive potassiums and 1 negative chloride, 3 net positive charges, but the right compartment, which we want to pay attention to, has only 5 potassiums but 8 chlorides, that is 3 negative charges. There are the 3 extra negative charges. The large negative charge in the right compartment now acts to attract back into the right compartment any potassiums driven into the left compartment by the concentration force. Watch. One goes in and is attracted back. One is driven out by concentration, one is attracted back by the negativity. In other words, the concentration force driving potassium from the right into the left compartment is now balanced exactly by the electrical force, the negativity in the right compartment, that attracts the potassium back into the right compartment. One out, one in. One out, one in. The electrical force that exactly balances the concentration force is called the equilibrium potential. In this case, it is the equilibrium potential for potassium and is abbreviated as EK. One in, one out. There are 4 main points that explain the buildup of charge separation. The first is the semi-permeable membrane. You've got to have a semi-permeable membrane in order for a system like this to work. In this case, the membrane is permeable only to potassium. The second is the concentration difference between the 2 compartments. There has to be a concentration difference of some ion between the 2 compartments. And the third is the concentration force that drives potassium from the right to the left compartment, thereby transferring a positive charge from the right to the left compartment. Watch. It transfers a positive charge. It moves one from the right to the left. And the fourth point is the buildup of positive charges in the left compartment then acts to repel any further transfer of potassium from the right into the left compartment. Watch. It builds up, gets bigger, and then it repels the potassium back in. Or another way of looking at it is the negativity on the right side attracts the potassium back in. The two are equivalent. So it is intuitively obvious that the larger the concentration force driving potassium from the right to the left, the greater the electrical force has to be to drive an equal number of potassium ions from the left to the right. Greater concentration differences of the permeable ion results in greater concentration forces driving the ions, which in turn requires a greater electrical difference to balance the concentration force. So for example, in the container in the top left, there is a very small concentration difference of potassium between the left and the right compartments, and hence there would be only a very small electrical difference to balance that particular concentration disparity. On the other hand, in the bottom figure, there's a very large difference in the potassium concentration. Hence, there would be a very large electrical force that would be required to build up to balance the concentration force. In the next movie, I will show you how to calculate the value of the equilibrium potential from the Nernst equation.